What's going on, guys? Last section we learned how to build our binomial models. This section we're going to learn the statistical tests to check if they're any good. Residual analysis. So the first residuals we're going to cover are our raw residuals, which is just going to be equal to our observed value minus our predicted value. So for our first observation, we had an actual value of y equal to 1, and we predicted 0.8 probability that y is going to be equal to 1. So a raw residual is just going to be 1 minus 0.8, which is equal to 0.2. For a second observation, the actual value was y, and we predicted 0.39 probability that y is going to be equal to 1. So a raw residual is just going to be equal to 0.61. Then for a third value, our observed value was 0, and we predicted 0.61 that y is going to be equal to 1. So we do 0 minus 0.61, and we get negative 0.61. And then finally, we had an actual value of y equal to 0, and we predicted 0.2 probability that y is going to be equal to 1. So 0 minus 0.2, and we get negative 0.2. Now our Pearson residuals. So the formula for our Pearson residuals is just going to be our raw residuals, and then divided by our pi times 1 minus pi. So this denominator term. So since we're working with a binomial distribution, this means that each individual observation follows a Bernoulli distribution. So the variance of our Bernoulli distribution is just p times 1 minus p. So we're just going to take the standard deviation of the variance of each of our observations. So each of our observations follow Bernoulli distributions. We're using square root of p times 1 minus p. Now if we were working with a Poisson distribution instead of a binomial distribution, where the variance is lambda, then our denominator would just be the square root of our lambda term, or the standard deviation. So our Pearson residual would become our observed minus our predicted value divided by the square root of lambda. But since it's binomial, we're working Bernoulli, so square root of p times 1 minus p. So for our first observation, the actual value was 1, and we predicted 0.8. And then our denominator is just going to be the square root of our 0.8 times 1 minus 0.8, and this will produce a value of 0.5. For our second observation, 1 minus 0.39 divided by the square root of 0.39 times 1 minus 0.39, and this will produce a value of 1.25. Then for our third observation, it's going to be 0 minus 0.61 divided by the square root of 0.61 times 1 minus 0.61, and we will get negative 1.25. And then finally, for our fourth observation, it's going to be 0 minus 0.2 divided by the square root of 0.2 times 1 minus 0.2. And this will produce a value of negative 0.5. So the third test statistic we can get from our residuals is going to be known as our Pearson chi-square statistic. And this is just going to be equal to the summation of the squared values from our Pearson residuals. So for our first Pearson residual, we got 0.5. So it's just going to be 0.5 squared, and then plus 1.25 squared, plus negative 1.25 squared, plus negative 0.5 squared, and this will produce a value of 3.625. So since this is a summation of residuals, in general, smaller values for a Pearson chi-square statistic is better. Deviance. So the first formula is going to be 2 times the maximized log likelihood of our saturated model minus the maximized log likelihood of our current model. So the saturated model just means that we have the same number of parameters as we have observations. So a result of this is that you're going to guess every observation perfectly. So what the deviance formula is telling us is what's the distance between our current model and the best possible model that we could build. So if we have a smaller deviance, it means we have a smaller distance between current model and best model. So this is of course favorable. Now if you have a larger deviance, then this means there's a large distance between current model and best model. But the problem with deviance, or chasing a low deviance, is that if you just keep adding predictors blindly, so if you add predictors blindly, your deviance will continue to decrease. So just like our r squared value, where if you're chasing an r squared just by adding parameters, you're ultimately going to end up with an overfit model. So the same thing with deviance, if you keep adding predictors, your deviance will keep decreasing and you'll ultimately end up with an overfit model. Now we're going to learn two different methods we can use to solve for deviance if we're not given the log likelihoods values, but instead just given the observations. So above we have our maximized log likelihood equation that we use to estimate our coefficient estimates. So for our saturated model, the formula would be yi times the log, and here we're just going to insert our predicted value for our saturated model. So since the saturated model always guesses perfectly, our predicted value is just going to be our observed value. So it's just going to be the log of yi, and then plus 1 minus yi times the log of, again, we're going to predict our observed value, or yi. So this whole side is going to be our saturated model for one observation. Now the second side is going to be yi times the log, and this is our current model, so it's just going to be our predicted value instead. And then plus 1 minus yi times the log of 1 minus our predicted value again. So this is our current model. So deviance is just 2 times, and then the difference between our saturated model, and this would be the saturated results for one observation, and then our current model, and this is the current model for one observation. So if we sum up the differences between our current model and our saturated model for each observation, we multiply that by 2, that'll give us the total sum of the difference between our saturated and our current model, log likelihoods. But right now this equation's pretty long, so how do we simplify this? So to simplify this, we can say 2 times yi times the log of yi minus the log of our predicted value, and then plus 1 minus yi times the log of 1 minus yi minus the log of 1 minus our predicted value. So essentially, whenever our y value is equal to 1, this side of the equation will activate, and whenever our y value is equal to 2, this side of the equation, and when our y value is equal to 0, this side of the equation will activate. So now let's do an example using this formula. So on the left here we have a data frame where we have one predictor, xi, we have the observed value, and we have our predicted value, or the probability that y is equal to 1. So if we use our formula for each of our observations and sum it up, it'll give us the deviance. So for our first observation, since the y value is equal to 1, only the left side of the equation will activate. So our formula is going to become 1 times the log of yi, which is just our observed value, or 1, and then minus the log of our predicted value, which is 0.8. So this is going to simplify to 0 minus the log of 0.8, because the log of 1 is 0. And this is going to be equal to 0.22. Now for our second observation, again the y value is equal to 1, so we're going to use the left side of the equation. So it's going to be 1 times the log of 1, and then minus the log of our predicted value, which is 0.39. And this will give a value of 0.94. Now for our third observation, now the yi value is equal to 0. So we're going to be using the right side of the equation. So for the right side of the equation, we're going to have 1 minus 0 times the log of 1 minus 0, and then minus the log of 1 minus 0.61. So if we simplify this, it'll become 1 times, and the log of 1 minus 0 is just 0, minus the log of 0.39. And this will give a value of 0.94. And then finally for our fourth observation, again, y is equal to 0, so we're going to be using the right side. So it's going to be 1 minus 0 times the log of 1 minus 0 minus the log of 1 minus our predicted value, which is 0.2. And this will give a value of 0.22. So now if we sum these values up, so 0.22 plus 0.94 plus 0.94 plus 0.22, and then we multiply them all by 2, this will give us our deviance value, which is equal to 4.64. So we just covered one method we can solve for deviance. Now we're going to cover a second method, where with this method we're going to solve for the maximized log likelihood of our current model and the maximized log likelihood of our saturated model separately, and then at the end we can just do 2 times the maximized log likelihood of our saturated model minus the maximized log likelihood of our current model. So first off, for our saturated model. So the formula for a saturated model, we're just going to use yi times the log, and then we're going to predict our observed value again because it guesses perfectly every time. So yi times the log of yi plus 1 minus yi times the log of 1 minus yi. So entering into this formula for our first observation, our yi value is equal to 1. So our formula is just going to be 1 times the log of 1. And since the log of 1 is just 0, this will produce a value of 0. So for our second observation, again y is equal to 1, so 1 times the log of 1, and this will produce a value of 0. Now for a third observation, y is equal to 0. So now we're going to be using the right side of the equation. So it's going to be 1 minus 0 times the log of 1 minus 0. So again, this is going to simplify to the log of 1, which will produce 0. And then for a fourth observation, it's going to be the exact same thing as observation 3. So again, we'll get 0. So we can say the maximized log likelihood of our saturated model is equal to 0. Now we can find the maximized log likelihood of our current equation. So the maximized log likelihood of current equation, the formula we're going to be using is yi times the log of our predicted value now, plus 1 minus yi times the log of 1 minus our predicted value. So for our first observation, our y value is equal to 1. So we're going to be using the left side of the equation. So 1 times the log of our predicted value, which is just 0.8. And this will produce a value of negative 0.22. For our second observation, our y value is equal to 1, and our predicted value is 0.39. So this will produce a value of negative 0.94. For a third observation, since our y value is equal to 0, we'll be using the right side of the equation. So 1 minus 0 times the log of 1 minus 0.61, which will be equal to negative 0.94. And then for our fourth observation, again y is equal to 0, so 1 minus 0 times the log of 1 minus 0.2, and we will get negative 0.22. So now if we add these values up, so negative 0.22 minus 0.94 minus 0.94 minus 0.22, we will get a value of negative 2.32. So the maximized log likelihood of our saturated model is equal to 0, and the maximized log likelihood of our current model is equal to negative 2.32. So if we plug these into our formula of 2 times our saturated model minus our current model, the formula will be 2 times 0 minus negative 2.32, and this will give us a value of 4.64, which again is the exact same value that we got when we solved it with our first method. So I think method 2 is easier, but if it ever asked what a specific residual is, such for a certain observation, then you'd have to use here method 1. And here, at the end I multiply by 2, but say if it asks for a specific residual for observation 1, so it asks for the deviance residual of observation 1, the value would be 0.22 times 2, which is equal to 0.44 for our first observation. And another thing to note, when we use our binomial distribution, notice that our saturated model, the log likelihood is equal to 0. So this won't be the case for all models. This is only for when we have binomial and we're using this equation. If we're using something like a Poisson, the saturated model will not equal to 0. Now we can test if our deviance is statistically significant or not. So the value we got for our deviance was 4.64. So the null hypothesis is going to be that all parameters in the saturated model but not the current model are 0. And then our alternative hypothesis is going to be that at least one parameter in the saturated model but not the current model is not 0. So let's say we're doing a 95% confidence, so our alpha is equal to 0.05. So to test if our deviance is statistically significant, we're going to be using a chi-square table. So the degrees of freedom we're going to be using is degrees of freedom is going to be equal to the difference in parameters of our two models. So difference in parameters. So since our saturated model, you have as many parameters as you have observations, since we have 4 observations, our saturated model would have 4 parameters. So it's going to be 4 minus, and then our current model, we have 1 predictor, and then just the intercept. So it'll be 4 minus 2 will be our degrees of freedom. So if we're to find that on the table, it would be right here. So 5.991 would be our critical value. So if our value of 4.64 is greater than 5.991, then we reject the null hypothesis. So since 4.64 is not greater than 5.991, then we're going to fail to reject. So what this means is that essentially that we're not missing any more important predictors, because the difference between our model and the best possible model is not great enough to suggest that we're still missing an important predictor in our model. The next statistic we're going to cover is going to be our likelihood ratio test, which is going to be equal to 2 times the maximized log likelihood of our full model minus the maximized log likelihood of our partial model. So you can only use this when one model is a subset of the other model. So let's say we want to compare the models of 2 times, and we're going to have beta 0 plus beta 1 plus beta 2 for our first model. And the second model is going to be the maximized log likelihood of beta 0 plus beta 1. So notice, this is essentially the exact same thing as a t-test, where we're asking the question, is this one parameter significant or not? So this would be the same as our t-test. So our null hypothesis is just going to be, is beta 2 significant? Or is beta 2 equal to 0? And our alternative hypothesis is beta 2 not equal to 0. Now if instead we want to compare the models of beta 0 plus beta 1 plus beta 2 plus beta 3 and beta 0 plus beta 1, then this is essentially the same thing as a partial f-test. Where now our null hypothesis is going to be that beta 2 is equal to beta 3 is equal to 0, or our alternative hypothesis, which is at least 1, of beta 2 or beta 3 is not equal to 0. And then finally, if we want to compare the models of 2 times, and then if we had all our parameters minus our null model, this is essentially the same thing as an f-test, where a null hypothesis is just going to be all parameters are equal to 0, alternative hypothesis at least 1 not equal to 0. So with our likelihood ratio test, we're able to cover both what a t-test would look like, where we're checking if one parameter is statistically significant, a partial f-test would look like by comparing two parameters, and our basic f-test where we're saying are any of the parameters statistically significant. So a likelihood ratio test is like a one-all do-all for if we have a generalized linear model. So let's say we're given two models, model 1 and model 2, and we're asked to find if beta 2 is statistically significant. And we're given their two deviance values of 2 and 6. So in order to find if beta 2 is statistically significant, we need to perform our likelihood ratio test. So how do we get our likelihood ratio test from two deviance values? So to do this, the deviance formula was equal to 2 times our saturated model, and then minus our current model, which I'll just call model 1. It's going to be equal to 2. And then on the right, 2 times our saturated model minus our current model, or model 2, is going to be equal to 6. So since model 2 is just a subset of model 1, they're going to share the same saturated value. So in order to get rid of this term, we're just going to subtract these two formulas from each other. So if we do 2 times our saturated model minus our model 1 is equal to 2, and we do 2 times our saturated model minus our model 2 is equal to 6. So we're going to subtract these two from each other, and we're going to end up with 2 times the maximized log likelihood of our model 1 minus 2 times the maximized log likelihood of our model 2 is going to be equal to 4. So if we distribute out this 2, we're just left with 2 times the maximized log likelihood of model 1 minus the maximized log likelihood of model 2 is equal to 4. So this is just going to be equal to our likelihood ratio formula, which was 2 times log likelihood of our full model minus the log likelihood of our partial model. So notice model 1 is our full model. It has an extra predictor compared to model 2, which is just one less predictor. So for our likelihood ratio test, we would use a value equal to 4. So now we can test if it's statistically significant. So we have a value of 4. And let's say we want to use an alpha value of 0.05. So again, this is just like performing a t-test. So our null hypothesis is going to be that beta 2 is equal to 0. Alternative hypothesis, beta 2 not equal to 0. So if we use alpha is equal to 0.05, our degrees of freedom is just going to be the difference between the number of parameters of our two models, model 1 and model 2. So model 2, we can see we had one predictor, one intercept. Model 1, we had two predictors, one intercept. So the difference between the number of parameters is just 1. So degrees of freedom equal to 1. So if we find that on our chart, 0.05, 1, we get 3.841. So we're going to reject if, and the value we got was 4, is greater than 3.841. So since it is, we're going to reject our null hypothesis. So we can say that beta 2 is statistically significant. Or you can say that our model 1 with the extra predictor is better than our model 2 with one less predictor. Now on to AIC and BIC. So an advantage of using these two statistics over the likelihood ratio test is that you can use these two statistics to compare models even if one is not a subset of the other. So if they're based on completely different predictors, you can still compare them using AIC and BIC. So the formula that we're going to use for our AIC is going to be equal to -2 times the maximized log likelihood of our model plus 2 times the number of parameters. So for model 1, our AIC is going to be equal to -2 times -20 plus 2 times the number of parameters, which we see is just 1, 2. And we're going to get a value of 44. And then for model 2, -2 times -10 plus 2 times the number of parameters, which we see is 1, 2, 3, 4. And we will get a value of 28. So you want to choose whichever one has the lower AIC, which we can see is 28. So model 2 is favorable compared to model 1 with AIC. Now for BIC, formula is going to be -2 times our maximized log likelihood plus the log of the number of observations times the number of parameters. So let's say we're given n is equal to 500, or we have 500 observations in our models. We'll say each of our models have 500. Then for model 1, our formula is just going to be -2 times 20 times -20, plus the log of 500 times the number of parameters, which we see is still 2, and we will get 52.43. And then for model 2, -2 times -10 plus the log of 500, and then times the number of parameters, which is going to be 4. Which will produce a value of 44.86. So again, you want to take the smallest value, so model 2 will be preferred with BIC 2. So the last statistic we're going to be covering is going to be our pseudo R squared. So the formula we're going to use is the maximized log likelihood of our model minus the maximized log likelihood of our null model divided by the maximized log likelihood of our saturated model minus the maximized log likelihood of our null model. So from this, plugging into this formula, we're going to get a value that ranges from 0 to 1, with values closer to 1 represent a better fit. So higher values are preferable. But again, just like our R squared value, you can ultimately just keep adding predictors to increase the value or the maximized log likelihood of your model closer and closer to 1. Until ultimately, if you have the same number of predictors, your model will essentially become the same as your saturated model, so you'd end up with a prediction of 1, just like your R squared value, which of course means that you probably have an overfit model. So now we're going to do an example. Say that your model has a maximized log likelihood of -10, the null model has a maximized log likelihood of -40, and your saturated model -2. So just by plugging in, you're going to get -10 minus your null model, -40, and then divided by your saturated model minus your null model, and this will produce a value of 0.79. So that's a pretty high pseudo R squared value, so it's probably a good model, considering if it doesn't have a ton of predictors. So that's going to wrap up this section. This entire chapter in general has pretty crazy formulas, so I'd say pretty much just try to memorize the main ones like likelihood ratio test and deviance, and mainly just know what they all mean. Like likelihood ratio test is just like a t-test, a partial f-test, whether or not to drop predictors and such. But other than that, I hope you enjoyed, and I'll see y'all next time. Thanks.